Hi, I'm Luffina. I'm a second-year PhD student in Dr. Jafari's Embedded Signal Processing Lab at Texas A&M University. Before I came here, I had a master's degree from Georgia Tech. My first signal processing research experience started in the RLE lab at MIT. Later, I combined my optimization skills learned from Georgia Tech and my healthcare experience with Harvard Medical School into this research topic. Today, I'm going to talk about the research topic of a graph-based method for interbeat interval and heart rate variability estimation featuring multi-channel PPG signals during intensive activity. It is a truth universally acknowledgeable. Average heart rate is one important factor in cardiovascular health monitoring. However, heart rate variability can provide integrated information of the cardiovascular and the autonomic nervous systems, which controls heart rate and blood pressure in response to physiological changes, such as respiration, exercise, physical stress. Studies have shown that heart rate variability is an important predictor and a prognostic factor for cardiovascular disease. Also, heart rate variability has been used in the research to study the cognitive load of surgeons and drivers. HRV is a measurement of variation in time intervals between successive heartbeats, which could be analyzed from interbeat intervals. For example, this is an ECG signal with 4 interbeat intervals. Usually, the interbeat interval is different from beat to beat. Traditionally, interbeat interval is measured by ambulatory ECG, which requires electrodes to attach on chest. This is the golden standard in clinical practice. However, it's really bulky and inconvenient to use in daily life. Given a recent trend for integrating health assessments into wearable technologies, more and more commercialized wearable devices are equipped with PPG sensors. The advantage of PPG wearables is that they are portable, non-invasive, low cost, simple and flexible to use. However, PPG signals are susceptible to motion noise. In daily life, there are different kinds of physical activity that will induce motion artifacts in PPG, such as jogging, running, typing, which lead to corrupted morphology. For example, when motion artifacts are added to clean PPG, it generates distorted waveforms. It is very difficult to tell the true peaks from the noise spikes. In addition, even in clean PPG, interbeat intervals change beat by beat, and it is non-consistent over time. Hence, heart rate variability estimation is more challenging than average heart rate from PPG signals. At the beginning, researchers focused on average heart rate estimation from noisy PPG. The techniques included troika and particle filtering. Later, researchers noticed the importance of heart rate variability and started focusing on IBI and HRV estimation from clean PPG. For example, Natarajan et al. Used a dataset of 8 million subjects to benchmark the IBI and HRV for different genders and ages. This is the largest dataset to date and shows great agreement of IBI and HRV estimation between PPG and ECG. However, their work removed all PPG data with motion artifacts. A recent study was on IBI and HRV estimation from noisy PPG. Egan et al. Modeled the IBI estimation problem into a shortest path and received median high correlation on a noisy PPG dataset. However, since weight assignment has a great impact on which path will be selected, the exponential penalty function they proposed limits the power of shortest path algorithm. The objective of this paper is to accurately and efficiently estimate IBI and HRV using motion-corrected PPG signals to improve diagnosis power. The main contribution of the paper are two. First, develop a graph to model multi-channel PPG signals. Second, formulate a convex penalty function to optimize weight assignment in the shortest path algorithm to attain high accuracy IBI estimation. This is the model overview. I first upsample and bandpass filter two PPG channels, and then I extract the morphological features of PPG. Here, I use systolic peak as an example. For each feature, I merged the diffusion points from two channels. Since the end of each heartbeat is the beginning of its next heartbeat, and they are continuous in time domain, I construct a directed acyclic graph where the vertex represents the candidate heartbeats and the edge represents the candidate interbeat interval. Then I proposed a convex penalty function to assign weights into edges, and later run the shortest path algorithm in this graph. The selected vertices in path represent the true heartbeats and are used to attain estimated interbeat intervals. Here I assume the heartbeats detected in PPG should highly match the heartbeats in ECG. So I extract the systolic peaks in PPG by detecting the local maximum in the time domain to calculate the interbeat interval. In parallel, I extract the R peak from ECG to attain the interbeat interval as the ground truth. I observe the corresponding diffusion points of true heartbeats between PPG1 and PPG2 have smaller time intervals than those false diffusion points induced by noisy signals. So I use this to design my model. I first label the nodes with different colors. For example, nodes from the first PPG channel are blue and the nodes from the second PPG channel are red. Then I concatenate the vertices from two channels and sort them by time steps. This is the neighbor selection step in graph construction. I first use the average IBI to attain T interval for each vertex I. For those vertices within T interval, I regard them as neighbors of VI and link those vertices to VI with directed edges. Then I need to assign weights to each edge. This convex penalty function is the highlight of this paper and brings nice results. I first set up a VI prime, which is the expected timestamp of the previous vertex of VI. Then I calculate the distance Dij between VI's neighbors and the VI. To attain the convex property, I apply the power function to calculate the Wij and then assign the Wij as the weights of those edges. I apply the shortest path algorithm in this directed acyclic graph. And this is the formula to assign weights into vertices. For the path that has a minimum weights, it has minimal total deviation from the true IBI. The backward search will select the vertices on the shortest path and regard them as the diffusion point of true heartbeats. The time difference of the successive selected vertices are regarded as the estimated IBI intervals. In ECG, I extract the candidate R peak and repeat the same process to construct the graph and get the interbeat intervals, which regarded as the ground truth. To be able to apply interbeat interval estimation on each feature of PPG, in addition to the systolic peak, I also extract the candidate maximum slope and onset, and then construct the graph by picking local maxima of the first derivatives and the second derivatives on the PPG signal. I tested the performance of my algorithm in the 2015 IEEE signal processing cup dataset. The subjects were running on the treadmill with changing speeds. For each subject, there are 2-channel PPG signals and 1-channel ECG signal. Results shows that my algorithm is strong. In terms of Pearson correlation, my convex penalty function outperformed the exponential penalty function in single-channel and the 2-channel model. Also, my 2-channel model provided 0.9 correlation for all 3 features, and the onset feature achieved the best performance of 0.939 correlation. In terms of mean absolute percentage error, my convex penalty function also provides a lower error than the exponential penalty function. Also, my two-channel model provides low percentage error of all three features, and the unsafe feature achieves the lowest percentage error of 4.33%. Compared to the state-of-art approach, my best result improved the percentage error by 43.5%. Finally, I evaluated the performance of HRV parameters in the time domain. I achieved a high correlation and a low percentage error. In short, the two-channel model outperforms the single-channel model, and the convex penalty function outperforms exponential penalty function. My best result could achieve 0.939 correlation with low percentage error 4.33%. Based on that, my algorithm could further be applied to measure IBI and HRV while people are typing or driving in future work, or it could also be used in clinical practice to improve cardiovascular disease prevention and healthcare monitoring in daily life. Thank you very much.